Hello students. So, in continuation of the code generation mechanisms and their properties, today we will continue with the OVSF and the Barker codes. Remember one thing that when we choose a code in practice for a typical kind of application, we see different kind of the advantages and disadvantages involved in a different kind of the codes, and the choice of the code for a typical application is largely depends on their two basic properties. One is the auto correlation and another is the cross correlation properties. The auto correlation function, as we have already discussed with respect to your random binary sequences, will be revisited and will be recalled. And autocorrelation function is defined as a very scalar product of the code signals, where actually the signal may be shifted by a amount of the delay tau. And remember, if I am shifting it by an amount of the delay tau, and the autocorrelation function for all the tau apart from tau equal to 0 should give us a 0 value. And so, I should get if I autocorrelate one sequence C, I mean PNC spreading sequence C with delayed version of this C, which I am writing at C tau. Tau is talking about the delay of that sequence. So, suppose this is the first sequence C and this is the delayed version of that sequence C. So, if tau is not equal to 0, so for all those cases I should get the autocorrelated value to be exactly 0. So, I should get basically, but the demand is for tau equal to 0 you will get a very good cross correlation autocorrelation value, and for the rest of this part you should get a complete 0 value. So, this is the ideal situation of the demand to have to declare that the code is having a very good autocorrelation property. Such a good kind of autocorrelation property is required in what kind of the scenario? Let us see. Suppose in radar or in any positioning system, localization is designing a system for precise localization, where the autocorrelation, this kind of autocorrelation process is utilized to detect the location, and where the autocorrelation process is utilized to extract the propagation delay for radar, and positioning system also to you wish to understand actually the typical delay value from where you will extract the location information. The high autocorrelation value and the rho and the very approximately 0 autocorrelation other values for tau not equal to 0 will be earnestly required. In a mobile communication also, for separating the different propagation paths, for example, I have a transmitter and I have a receiver here, and I am transmitting from the transmitter to the receiver, and via different paths the signal gets received in the receiver, and the point who are actually helping to scatter the signal in the environment, we call them the scatterers. So, the way this movement is going on is like this, propagation is going on is like this. The same signal is get scattered by the scatterers who are located at a different position, and they are also reflecting the scattered they are scattering the wave and they are reaching to the receiver front end. So, you are not only getting the direct line of sight path, you are receiving the signal via the scattered paths. So, if we wish to understand the delay and hence the delay associated with the direct path and all other scattered paths, they are not same. If we wish to segregate the paths, multipaths, actually the signals which are received in the multiple paths, if there is a requirement to segregate all of them, we have to actually estimate the corresponding delays independently. So, for such kind of the situation also, the high autocorrelation peak, spreading sequence with high autocorrelation peak and the having perfect autocorrelation property is earnestly required. Think about a CDMA system, where the different code signals that we already have discussed during Warshad code analysis, that in a multi-user scenario where code division multiple access is utilized, where actually different users are given the independent codes, orthogonal codes, and they are separated out, they are segregated in terms of all those unique codes allotted to them. and if the different code signal C and C prime we are denoting here is utilized, then they will be utilized to distinguish between the different connections. And also the mutual interference in such a situation, when the connection is done, the mutual interference from C to C prime, which is proportional to the scalar product of the C and C prime. And for the orthogonality, to maintain all this, we need perfectly actually the codes to be orthogonal to each other. So, good autocorrelation property is there, and good cross correlation property will be in demand when my two codes, two different codes assigned to two different users, and when they are having a scalar product, the product output of the product we are expecting to be exactly 0. So, the codes who are having these two kind of the properties are the theoretical speaking is the best code of the demand, but unfortunately the codes simultaneously having a very good autocorrelation property and a very good cross correlation property, simultaneously having both of them is almost impossible actually, and that is why sometimes we will find that we need to compromise actually in between the selection of the very good, either very good autocorrelation property codes or very good cross correlation property codes based on the kind of the application for which they will be used for. See that when we are talking about the code division multiple access systems, and we are thinking that multiple users will be there in the network, and each of them will be given a dedicated orthogonal codes. So, and if you think that, then their interference between the users, the multi-user interference will be nullified only because of the orthogonality, maintaining the orthogonality of the codes itself. That is not the exact case, because as I have explained in the last slide, that when the signal is propagating via wireless communication medium, actually it not only traverses the line of sight path, it traverses from the multiple scattered paths or the multi paths. On the top of that, whenever hence the code signals that you are trying to transmit, they are not transmitted always also some synchronized fashion. So, because of the loss of the synchronization, and also because of the delays involved in the multipath propagation. So, both of the cases you will be receiving the signals who are delayed by certain amount from the generated signal at the transmitter, and hence you will be always demanding for multi-user environment, you will be also demanding that the cross correlation value should be minimized. So, in case of a multi-user interference, diminishing the multi-user interference, there are the two demands for the code. The codes should be orthogonal, chosen such a way that we will get a set of the orthogonal codes, and the cross correlation property within the set should be also minimized. And each of these known types of the codes, they fulfills one requirement to a higher and other to a lower degree. Means if your autocorrelation is very good, cross correlation won't be actually satisfactory, and if cross correlation is really very good, autocorrelation won't be satisfactory in such a way. And for your kind of the application for which you are selecting the code, you have to choose a code who gives the best compromise between the kind of the demand you are having. And so, choice will be application dependent and the service requirement dependent. And another method to apply the several spreading steps and use different types of the codes for the separate steps may be another good assumption. For example, the type of the codes you are utilizing for minimizing the interchannel interference may not be actually good to minimize the intersymbol interference. So, you may actually utilize a different kind of the codes to go ahead with. So, that will be the design with the multiple codes. So, concatenation of the multiple codes, spreading codes for the design. Today, as I mentioned, today our discussion point is orthogonal variable spreading factor codes. If you look the structure of this orthogonal variable spreading factor code, you will see a lot of similarity with the Walsh-Hadamard code, but the arrangement is little bit different. And we will be arranging here, we will be seeing here some tree structure getting formed for the orthogonal OVSF codes based on the spreading factor. The spreading factor is usually a power of 2. So, you will get the spreading of either 1 or 2 or 4, 6, 8 like that. So, the way the code is generated, it is in the following recursion process. Suppose you are generating a code of twice the spreading factor, where spreading factor value is varying from 1 to the higher numbers, and it is of 2m, and m can be having varying from 0 to SF minus 1. He will be constructed by CSFM and CSFM. CSFM is the previous one, means divided by 2. I mean, it means actually the previous stage values of the codes, and the next stage value of the codes will be constructed by the same previous step value, and its second position and the second location will be in the matrix will be of just the conjugate of that. We will take an example to have an idea how the course is, how the typical code is getting generated. But remember, this is the composition of the code C comma C here inside the vector bracket is the composition of the codes. The orthogonality of this kind of code for a fixed spreading factor SF follows the above defined equation, and the notation variable spreading factor results from the fact that they are applied in the CDMA communication systems offering different data rates. So, very good part of this kind of the code is you can generate the several codes under this family who are having the different value of the spreading factor. Based on the spreading factor, you are basically varying the data rate offered to the users. So, if you wish to generate and design a circuit where multiple data rate support is required, and orthogonality is also a very important issue in association with the protection against the jamming and interference control, OVSF codes find lot of applicability in that sense. So, we will take an example here. Remember, the total symbol, as we are not changing the chip duration and the number of the chips. So, the symbol duration of the generated code will be governed by this equation, where the symbol duration is equal to spreading factor multiplied by the chip duration. Let us take an example. We will start with the spreading factor 1. So, the code will be how? The code will be, the nomenclature will be C1 comma 0, because we understand we write the nomenclature as 2 SF comma 2 small m. Okay. We have started with m is equal to 0. Here, as the bit is equal to just 1, as SF value is equal to 1, and this is equal to SF value is SF is equal to just 1. So, it we are starting with the not 2 SF, it will be starting, at least the first one should start with just SF. So, this is the SF is equal to 2, and from SF equal to 1 you are generating SF equal to 2. So, here it will be working like this, 2 i's into SF of and comma 2 i's m, and the way you will be generating it like this. So, this plus 1 will be repeated for 2 comma 0, but 2 comma 2 m plus 1, this is 2 SF 2 m plus 1, the code will be repeated from the 2s from the SF, and then the second entry will be the complement of the last data entered. If I go ahead further, so from 2 next generated SF will be definitely 4, because it is the power of 2 you are proceeding. Here again this first 2 will be repeated, and the second location you have that same repetition. For 1 will be, as it is a 4, you will run from 0 1 2 3, because in every cases whatever the value of the SF you are having, m is varying from 0 to a maximum that number. It is a SF minus 1 up to that m can vary, as we have seen in the 1 point equation number 1.2. So, when SF was equal to 2, m has 2 values 0 and 1. For SF equal to 4, m has 4 values 0 1 2 3 for every SF equal to 4. So, C4 comma 0 is generated by repeating the C2 comma 0. C4 comma 1 will be the repetition of the previous one, and the complement last entry will be complement of that. C42 will be the repetition of the previous one, which one 2 1, and the last entry will be the complement of the remaining section. So, this way we can proceed. So, this is the T structure you are generating. Good part is that there is a data rate variation possible, because your within a symbol duration, the number of the chips that you are utilizing, they are varying. How see? And remember one thing, to establish some connections with the different data rates, some rules we have to follow here. And also to maintain the orthogonality, in order to maintain that there won't be any interference from the one kind of the user to the next kind of the user. So, the codes that we are generating, that should follow certain rule. What are those rules? Better to go to the next slide to understand the rule. So, we generated the sequences like this from C10, C20 generated, from C20, C40, C41 generated, and from C2, C42 and C43 generated. So, from each parent, one set of the new child processes or child codes are getting generated. Remember, if C41 is already allotted to some user, in order to keep the orthogonality and in order to keep that minimal interference property from the other user, you should not allow the code which are the child codes of this C41 or all the parent codes from where actually C41 is linked to the user, new user. So, give for this example, for C41, CH2, CH3, these are the child codes, they cannot be allotted, as well as his mother is C20, whose mother is C10 and C21 also. So, C41 is heavily correlated with 20, 10, 21, 82 and 83. So, this is his whole family. This family, or none of the members from this family, none of the code members from this family can be allotted to second user if C41 is in use, but you can allot any other codes from say C891 to this up to the 7 and C40, this will be 0, this is not 9. So, this is C8 comma 0. So, anybody actually any other guys from the child section or any other guys from the peer section can be chosen for allotting it to the second user. And how the data rate can be varied by using the different kind of the codes or something like that. For example, suppose some second connection which is having some twice the data rate requirement needs to be provided, needs to be supported, and then it has to select, if I have started already given the code C10 and if the second user is demanding double the data rate corresponding to the compared to the first user connection, then I have to give either C21 or C20, because within a period of one data bit of connection 1, connection 2 can transmit 2 bits. Okay. Because the structure, if you see, here actually you are transmitting 1 0 and here you are transmitting 1 and here you are transmitting 1 1. So, within the same bit duration, here you are transmitting twice the bits, here you will be transmitting 4 bits. So, the data rate, if you are trying to see from here to here it is double, from here to here it is double. So, from here to here it is 4 times. So, the data rate, variable data rate support in a CDMA network is heavily possible if we allot the OVSF codes and we choose the OVSF code in such a way that along with the data rate support, the interference cancellation to some extreme level is can be provided, heavily provided. So, the advantages, disadvantages of this kind of the code. The disadvantage of OVSF code is that if the orthogonality of the codes it is lost, then there is no perfect synchronization. The cross correlation values of the code increases heavily, which is not a very good situation for a kind of the CDMA network where multiple user support is required. But it has also very poor auto correlation property that limits its application sometimes for the kind of the application where your high synchronization, precise localization is required, and in the radar kind of situation where your precise estimate of the delay is to be done. So, neither it has a very good, I cannot say that it has a very good auto correlation property, and with minimal, with no synchronization, no perfect synchronization situation, you can provide you a very good cross correlation also. The summary is something like that. The OVSF codes can be applied to realize the connections with different data rates by varying spreading factors. So, different data rate is the main gain or main advantage of this kind of the codes, which is not supportable by any other codes that we will discuss today in the family of the codes. Orthogonality is preserved exactly even between the connections of the different rates. So, if you are that orthogonality that you are talking about, if under the perfect synchronization situation, definitely. And these two properties of this or OVSF codes have made them attractive for the modern communication systems like UMTS and IS-95. And with that we will end our discussion with OVSF here, and we will try to see some new family of the code. Our next discussion will be on the Barker codes. Barker codes, you will see they are utilized in the space spectrum communications because but for some definite kind of application. Barker codes are mainly utilized for the synchronization purposes inside the space spectrum communication, because we will see that the codes, available codes in the Barker is not much. They are very few in numbers available, because of which they cannot be utilized for mobile communication system where the dense number of the user support is possible, nor actually the length of the codes, even not only the number of the codes are less, the length of the codes that are available, that are also not remarkably high. So, they cannot be utilized for the code keying purpose, or they cannot be utilized for the spreading sequence purpose to avoid the jamming effect and all, but these codes are very useful for synchronization purpose. So, that is why we will go revisit its property. Barker codes are characterized by minimizing the certain kinds of the reduced autocorrelation function. So, the autocorrelation function that a Barker code has to follow, has to satisfy to declare a code to be a Barker code, the two autocorrelation functions are this. So, the delay that you are having, if the nu is the delay or the shift, the lag over which the autocorrelation you are computing, if the lag is positive lag between 0 to m, then the computation will go like this, the equation 1.2. And for the negative lag, and capital M is the length over which actually you are doing this performing this autocorrelation, the length of the whole sequence, and its autocorrelation property for minus m to the 0, I mean with the negative lag values, that will be governed by the equation 1.3. The code here always consists of +1 and -1, and its length is assumed here to be capital M. The code can be said Barker code with all this autocorrelation property if and only if this relation holds good. That is the autocorrelation value should be always less than equal to 1 for all the lags, where the lag is varying from mod of the lag varying from 0 to m. So, for both the equations that we have discussed earlier in the last slide, for equation 1.2 and 1.3, both the cases actually the output of the autocorrelation computation should be less than equal to 1 to declare the code is a Barker code. Correlating a Barker sequence B of length odd length m. So, length of the Barker sequences, remember that they can be odd or even. So, if I try to go ahead with the correlation of the Barker sequence of odd length with a concatenated Barker sequence of the form something like this, where alpha i's are equal to -1 and +1. So, what we have done is we have concatenated the Barker sequences, and which and they are trying to confirm the correlation property, and which occurs when the spreading sequence of the data bits, the out of phase values of the discrete autocorrelation function. It happens actually, this kind of autocorrelation happens when we spread the sequence of the data bits, and we are getting actually the raw Barker code in the receiver, and we are trying to find out the autocorrelation property of it. Then the out of phase values of this discrete autocorrelation function, I mean you can call it as a cross correlation also. It is the out of phase values which is not exactly means of exactly actually tau equal to 0. So, when this chi is going on, then the out of phase values for this autocorrelation function, it will be turned down to 1 by m and minus 1 by m. These are the smallest possible values that a Barker code can give you. So, the transformation is something like this, either C mu to minus C mu or C mu equal to minus 1 to the power mu into C mu, and C mu to minus C m minus u, where mu is the delay that with which we were dealing with. The Barker codes, available Barker codes and the generation of the codes are very small, and length number 11, Barker code length 11 is widely used in the WLAN sequence, WLAN standard is 02.11 standard, and not only in the LAN standard, in the several space spectrum communication system design, this Barker length of 11 is widely used for the synchronization purpose. These are the few Barker codes that I was saying that is possible to generate, and there are no other Barker codes available with the kind of property that we have already stated related to the autocorrelation and the cross correlation of this kind of the codes. If I follow all that, you will be able to find only the code with length 2, length 3, length 4, length 5, length 7, length 11 and length 13. So, hardly 7 number of the Barker codes you will be able to find for practice, and remember the Barker code number of very short length C2 and C3, they and C4 even, they are not having much use in practice, because even for the synchronization at least certain length of the codes will be required to provide the extract the to estimate the parameter of our interest. And if it is a timing, and if it is a timing extra, mostly for the timing extraction, the timing information extraction, we try to utilize these Barker codes. And then also actually you need a sufficient length of the chip, sufficient length of the codes, I mean the name of the chips over which actually the estimation needs to be averaged out. So, very small length of the codes like C2, C3 or C4 won't give you a very good estimate, because averaging cannot be done over large number of the chips, the available chips are so less. So, a very good kind of the synchronization is not feasible, because the estimate will be very poor if you utilize a very small length of the Barker codes. That is why I was telling that length number 11, length number 13, even length number 7 to some extent for a short distance kind of communication, Barker codes are utilized. For WLAN, this C11 as already mentioned, C11 Barker code is utilized for the synchronization purpose. So, Barker is not unusual, unlike the other kind of the applications what we have discussed at the beginning of the Walsh-Hadamard code discussion, that codes are mainly utilized for the code keying or multi-user support, and mainly for these two purposes, and also for giving the protection against the jamming environment, the interference cancellation. Barker is not getting utilized for any one of them. Barker is showing that code can be utilized also for the synchronization purpose, which is really very important task that we need to do for a successful reception of a space spectrum communication system, where code acquisition and the code tracking is of earnest importance for successful reception and retrieval of the data in the receiver. We will discuss this later, but the code that will be utilized now we have already discussed. Barker is that code.